Today with this. So after being here, as I said, for 5 years at UC, having this luxury, I went back to my post at the UN at ACLAC. And I learned all these new methods as well, these new modern methods that I didn't know before when I studied for the first time. And so going back now, I'm trying to figure out in my head as well how these new and modern methods that nobody knew 5 years ago or 10 years ago can be applied for development. And I found a bunch of methods that I get very excited about under this umbrella, which are called complex systems or complex systems theory. So there are several institutes around the world, in the Santa Fe Institute, others, Max Planck, Fraunhofer, that work with these kind of methods. And I wanted to talk to you a little bit about what they are and what I think their usefulness is also to development work, because also that's what I'm trying to figure out. How can we use these modern new methods to increase, to improve development work? So this has a history. The context of complexity comes. There was a paper written in '48 by Moore and Weaver, and he basically said, well, there are 3 kinds of problems. Before the 1900s, science was basically concerned with 2 variable problems, right? Temperature and pressure, population and time, production and trade and so forth. So these were basically problems of simplicity. They had a complexity level that introduced 2, 3 or 4 variables. Then during the 1900s, a whole bunch of science developed methods to work with what we call disorganized complexity. During the 1900s, there's basically probability theory and statistical mechanics came up with methods that allowed us to create averages, to measure variances, and all these what we now call statistics came about it, right? Regression analysis, statistical methods. And they work very well when you have a very large numbers of variables. However, you need some assumptions for them to work perfectly, and they also always have to be IID, independent and identically distributed. So it's a very large number, but they have to be independent, for example. And then these methods, which we call statistics, regression, structural equation model, and so forth, econometrics came up, work very well in these kind of cases. However, they said there's a third part of problems that deal simultaneously with a sizable number of factors which are interrelated into an organic whole. They cannot be handled with the statistical techniques so effective in describing average behavior. And this is a whole third kind of problems that he said science of NASA over the next 50 years learn how to deal with these problems of organized complexity. That he said that 65 years ago, and we still didn't hold up to his demand. So he also brings up some examples of these kind of problems. He says, for example, on what does the price of wheat depend? That's a problem that has a sizable number of variables in it. However, they're all interrelated into an organic whole. And if you want to understand this kind of mechanism, we need different kind of tools. Statistics doesn't help us, and working with 1 or 2 variables is also too simplistic, right? How can we explain the behavior pattern of an organized group of persons? I will show an example today. You know, then riots break out, for example, or diseases spread. So these are models that of organized complexity. Economic control to prevent wide swing from prosperity to depression. How can we do that? We obviously do not understand that yet. Otherwise, we wouldn't have had so much problems in 2008 and still. So these are problems that they have the selfish interest that contribute to a stable, decent, and peaceful world. So these are problems that cannot neither be handled with simplicity, simple models, but also not with average behavior. So historically, always these complexity science, we always often associate it with ants. So there's this very famous book of Gödel, Escher, and Bach, where we basically analyze ants because they're much simpler to understand than human societies, and you can learn a lot from complexity studying animal behavior. Here, this is one example where we come from. Obviously, if you look at social systems, they look very complex, right? They're not all independent, identically distributed beings, but it's a complex system. It's a sizable number of variables. They're all interrelated and they're interdependent. So complex systems basically are characterized. I personally, right now, I teach this class here next door every morning, and we talk about 6 different characteristics of complex systems. First of all, the variables or the subjects are not independent. First of all, they are connected. So there are different tools I can use to handle these different characteristics that I cannot do with traditional tools. One tool is what I talked about here today is social network analysis. That helps you to work with systems. It's a method, helps you to work with systems whose agents are connected. The other one is they're interdependent. Interdependent is different than connected because, well, they can be connected but actually don't affect each other, so it's more like the strength of the tie. Or they can be connected and influence each other a lot. Complex systems influence each other a lot. And that leads to disastrous results for an analyst, because that leads to that the entire fitness landscape, what was good now, can be bad later, right? So this fitness landscape, we say, dances because of the interdependence between the actors. Then the agents are diverse, which is something the traditional models usually also don't work with. They're very diverse agents. We usually use aggregate behavior. We average out the diversity. However, diversity is very important if you want to explain these famous tipping points, or if you want to explain how feedback loops go together and create runaway systems or create stable systems. So diversity is very important. Then these complex systems process information. They are adaptive. A lot of evolutionary techniques are helpful to analyze that, and they're path dependent. That came from chaos theory, from dynamic systems theory, so they depend on where they come from. And traditional models also don't help us with that, because traditional models, we don't actually look at where models come from. They should work right now, and they should work then later, and work for every country or for every society. And in complex systems, we find out, actually it matters where you come from. And at the end, they're emergent. Emergent is a very fancy, very sexy term that is often used. Basically, the technical term for that would be non-linear. They are non-linear. They have non-linear behavior. And I will talk about that a little bit. The interesting thing is, so these are the characteristics of what we now understand of complex systems, or when we call them complexes, when they have all these 6 characteristics. And there are different tools, modern analysis tools, that we can use in order to harness these things that traditional analysis, statistics, or so forth, simple models cannot allow us to do. I will talk about these two now for the next half an hour, a little bit, not of all the others, but of these two, and show you 2 different tools, analytical tools. One is social network analysis, and the other one is agent-based modeling, computer simulations. This helps you to harness these 2 characteristics. So the social is equal to a network, right? If I talk about social systems, I don't talk about a bunch of individuals which are all independent. I actually talk about the definition of social is that there is basically a networks we have to do with each other. So, and then we can also, well, draw out these networks. This is, for example, a friendship networks by race. As you can see, the white kids hang together with the white kids, and black race hang together with black kids. So this is by race, and you can see that the network structure helps me a lot to understand what's going on in this school. And then you can analyze the networks. For example, here there are different bridge builders, for example, that build the bridges between the races and so forth. Now, everything is basically a network. Every social phenomenon. This is a terrorist network, very famous. These are innovation networks. So this is an industry. You can see in Boston and the Bay Area and in San Diego, that's the development of the biotechnology industry. In Boston, in the Bay Area, and surprise, surprise, they develop according to a network around the leading universities. So in Boston, it's Harvard, MIT, and the Bay Area, it's Stanford, and around them, these innovation clusters build. So if you analyze the networks of investment, of collaboration between them, you can really see how these these clusters, industry clusters, grow. And that's what an industry is, right? It's a network of different agents that cooperate, all compete, and with that grow. Then you have here a food network, for example, very important. It can also be a food network, biological network. Here in politics, we have a network of political integration or cooperation, which are, of course, networks which we talk about all the time. You can also draw them out and analyze them. Here you have an international trade network, an investment network, very important, who invests into whom, which company, that's also a network at the end. A transport network, a migration network is, of course, a network of sustainable development. Business strategy is very important. If you draw the network of boards of directors, for example, who sits in which boards of directors, that will give you a network, and with this network you very quickly understand how a country works, right? Because it's very few people who create a network and sit on different boards of directors. You draw that out, you analyze it, it's a very active area of research because it has been so successful to draw that out, and that's basically networks, right? Here you have a democratic governance network, which is basically who provides financial support to whom in which campaign. And you can also see, of course, that's a network. You draw that out, you understand why this campaign has this focus and why that campaign has that focus by, in this case, financial flows from the one to the other. And actually also happiness, to show you the last one. We also found out that this is contagious. Even happiness goes through networks. Same as a disease diffuses through networks, and innovations diffuse through networks, also happiness diffuses through networks. You tell me if your friends are happy, and I'm going to tell you if you're going to be happy. By the way, many other things as well that we don't think. Obesity is also contagious, and many other things. So we can show this when we analyze network structures, because society is as much about who you are as it is with whom you are. And in the last couple of decades of social research, we focused a lot about who you are, and we characterized you by your educational level, by your income, by your capacities, by your whatever, and then we did statistics with it and draw conclusions, but we never ask about with whom you are. And ask your mother, she would tell you, be careful with whom you are, because that, so it is very important, right? And now science starts to make a science out of that, out of this simple motherly insight. And of course, Manuel here hit the jackpot by writing the right books at the right times. In the 90s, he wrote that already and explained as well, guys, think about networks. And with that, he won the Nobel Prize of Social Sciences, let's say. Okay, so why is networks so important? As said, because society is as much about who you are as with whom you are. And I give you here one example I worked a lot with, and you can see the difference of these. So why social networks are so important. The traditional analysis, I worked a lot with the diffusion of innovations. For example, how computers and cell phones diffuse in society. And you have here a society of 8 people, and some of them have computers and others don't. So what you do as a social science researcher, you try to find a signal in the noise, or you try to find patterns, and you say, well, it seems that computers go together with education, right? There are some guys educated, others not, and they seem to have to do something with each other. So what I do is I count how many have education and computer, and how many don't have education and computer. So 3 have computer and education, 1 has a computer and no education, 1 has education and no computer, and 3 have the other way around, right? And then what I do is I put this up here, I build square differences to the mean, that's how we do that, least square. Then I put a line through it that minimizes these distances, and that's what we call a regression. And then I have a positive correlation between education and computers. Now, I can make a policy out of that, right? And say, well, education has something to do with computers, I showed that, and I showed this correlation was significant. It certainly, I don't know, my battery went up. It certainly doesn't have anything to do with red pants, right? I can do the same thing for red pants. There's 1 with a red pants who has a computer, 1 that doesn't, then 3 of them with computer, 3 without. I build my squares to the mean, I put there. And certainly, like, there's no correlation, no positive, no negative. I mean, red pants don't have anything to do with computers, correct? So my suggestion would be, Mr. President, please make a policy that has to do with computers and education, because these 2 go together, right? That's what I guess. Now the problem is innovation doesn't fall like manna from heaven and hits us like homogeneously. Innovation actually diffuses, and diffuses through social networks. And what we often found when we do this kind of analysis is that we have this kind of network structure that looks kind of like this. That's what we often find. And we find that if we want to diffuse this technology, actually there's a missing link here. If I would close this link, actually the technology can diffuse much quicker. And once I have this kind of picture, actually it makes sense for me to make a policy on the guys with the red pants, because these are the innovators, these are the agents of change, that's why they have red pants. And if I convince these 2 guys to collaborate, this technology can diffuse through my social network, and I can, with an intervention of only 2 people, lead the innovation to all 4 of them. Otherwise, I would have to make a policy, a generic policy on all education, right? Why didn't I get this insight? Because I didn't have the information about these blue ties. The same happens the other way around for the diffusion of a disease. In the diffusion of a disease, you want to cut this part here, right? You want to vaccinate exactly these bridge builders, because then you can stop the diffusion of the disease very efficiently. Again, there are 2 options. Either I vaccinate everybody, I vaccinate 50% of society, and then hope I get lucky. Or I know the network structure, I identify who are the bridge builders, and these are the ones I vaccinate. So with vaccinating a couple of thousand people, very efficiently, I can stop the spread of the disease. Usually these bridge builders are nurses, bus drivers, bank clerks, the people who are in contact with many other people, right? They can stop the spread of the disease. So the network structure tells me a lot about this diffusion phenomenon, for example, something that I wouldn't have known before, and then I can make policies much more effectively. Why? Because now I have additional information. However, I do need additional information. So what we usually do, I need information about these blue ties. So traditionally, what we do is when we analyze a society, we have a society with different agents, and then we describe them, and we create these databases. At the UN, we are full of these data. You create these databases like nobody's business. There's countries with all the attributes, household survey, census survey, employment survey, whatever you want. You can describe everything you want. But what we assume is that society looks like that. They're all independent guys. Now, society doesn't look like that, actually. Society, they have some kind of connection, and that's actually what makes a society, right? And therefore, we have to collect this kind of data as well. And this data is a completely different database that we do not collect yet. So what this database basically shows you, you have Jorge here and Jorge here, and then Jorge connects to Maria. Okay, so Jorge connects to Maria. He doesn't connect to Juan, but he connects to Magda. Okay, perfect. Magda connects to Jorge, yeah. She connects to herself, makes sense. Maria to Maria. She doesn't connect to Juan, but she connects to Maria, connects to Magda. Right? So I create this in this database, in this matrix, and now I have two databases which are analyzed together. And I get much more out of it, much more out of it. But we do not create these databases yet. Right? So we do science for the last 50 years with half of the story. And we still dare to call this social science. Actually, it's kind of a bunch of people who don't have anything to do with each other. So this argument of networks is of course very important. So you first have to start to collect this data. Is network science got a big boost over recent years for two reasons. First of all, these databases are very information intensive, very data intensive, and our computers weren't able to run them 10 years ago. So the new computers are able to run them. Second of all, we have to collect this data. And that's the same pain as we did for the last 50 years, creating institutions who collect that data, right? So we created national statistical institutes, national statistical offices, surveys here, surveys there, trained, but we did a lot of effort to create this data. However, now you want us to do that again with this one here, right? So a positive coincidence is that this data often nowadays comes basically for free because we started to digitize our connections. And if you have digitized connections, they get registered, and then I can just retrieve it from the web. So Facebook gives you a lot of this information. Twitter gives you a lot of that information. And that gave a big boost to network science. And the guys who have this kind of information are new billionaires, right? Zuckerberg. He doesn't have billions of dollars because he has a genius software. The software costs a couple of $100 if you want to reprogram it. He knows who's with whom. And with that he has a lot of intelligence and nobody else knows. Right? So digital interaction gives you this insight. You can have the same thing between companies, between countries, trade networks, and so forth. And that gave a big boost in the last couple of years, the last 5 years, where you can now produce a whole bunch of intelligence about social behavior that you couldn't do 5 or 10 years ago. So these are the two big things that gave a push to network science. Alright, so that was the first. I said complex systems are connected, and it's important that we analyze that. And I said in the last, I said a couple of other characteristics. Complex systems are nonlinear. They have emergent phenomena. That's a much cooler word for it. So what is emergence? Emergence, social emergence, is actually at the heart of all social sciences. It always has been. If you think about Durkheim, the father of sociology, he was fascinated. He wrote this entire book about suicide. He said, how funny is that? Then I can predict exactly how many people will commit suicide tomorrow in New York. And how many people will commit suicide next week in the United States. It's not like somebody says, hey man, we have to fulfill this statistics, I'd rather kill myself tomorrow, not the day after, because otherwise, no. It's really something nobody intends. As crazy as suicide. Nobody really tries to organize that, or nobody really tries to contribute to that. However, it is a very stable social emergent phenomenon. The suicide rate is stable. He wrote an entire book about that, and that was the founding father of sociology. You have that not only in sociology, of course, also in economics, the economists. Right? Adam Smith, the invisible hand. He intends only his own gain, and he is in this, as in many other cases, led by an invisible hand to promote an end which was no part of his intention. By pursuing his own interest, he frequently promotes that of the society more effectively than when he really intends to promote it. So we are all selfish egoists, but somehow prosperity comes out of it, sometimes. So that's when the invisible hand works, right? And Adam Smith was fascinated by that because you didn't see any of these mechanisms on the individual level, but the total is different than the sum of the parts somehow. Then you have this in political science as well, Rousseau, who taught us that the sum of the volonté particulière is different than the sum of two is different than the volonté générale. So the sum of the individual wills is different than the general will. So, for example, I want to drive fast on the freeway, Tom wants to drive fast on the freeway. If we both drive fast on the freeway, we're going to kill ourselves, so we want a speed limit. So the sum of our individual wills, I want, he wants, is different than what we want. So the we is different than the sum of the I and the I. And that's Rousseau, right? And that's why I say you need discourse in democracy, because the general will cannot be identified, the general will has to be created. Why is the I, and then you can also write in, you'll see where the emergent phenomena comes from. If I want to drive fast on the freeway, and you want to drive fast on the freeway, that's cool. However, if we all go on the freeway, what happens? Interactions, interdependence, and that messes everything up, right? So summing up our individual wills in this case does not consider the interaction that emerges, and that completely leads to a different dynamic. So through interdependency, through interaction, the total is different than the sum of the parts. And that's political science. So we have sociology, economy, political science. Oh, of course, and this gentleman who did everything together. And he wrote this down, which is called the basic metaphysical principle of dialectics. Merely quantitative differences beyond a certain point pass into qualitative changes. So that is basically what he says. That's a nonlinearity, a mathematician would say. That's an emergent phenomena. You have a quantitative difference, and you keep on going, and everything is fine, and then suddenly, boom, something completely different happens. Nonlinearity is the same, for example, it comes from physics, a phase transition. When you have water, then you have water and water and water and water, and then suddenly at 100 degrees Celsius, boom, it becomes vapor. And then you have water and water and water and water, and 0 degrees Celsius, boom, it becomes ice. Right, so these nonlinearities, these phase transitions, these tipping points, these large events are nature to all kind of systems, and in social sciences as well. So merely quantitative differences beyond a certain point pass into qualitative changes. So how can we imagine that? So that is long around in social sciences, and we know, and that makes it fascinating, and that's why we are fascinated with social systems and want to study them. So how can we get a handle of it? How can we harness it? I'll show you one way we can harness it, and maybe the best way, and that is through computer simulations. So we just simulate, we grow artificial societies and simulate that, and then these things will also emerge. This is here a model of Schelling, a segregation model. He said, well, actually many cities in the world are very segregated. That's Santiago de Chile, where I live right now, and it's very segregated. The interesting thing is, so, I don't know, there are Republicans and Democrats, there are, it's racially segregated as well, and whatever you want. Now, if you ask the people themselves, nobody there is really racist, or nobody is really all the people are very tolerant. If you ask them, say like, how many of your neighbors do you want in your neighborhood directly living next to you, which are also Democrats? Like, I don't know, maybe 1 or 2 people, maybe, I don't know, 50%, I don't know if the other one. How many of the people do you want to be of your same religion? So yeah, maybe 1 or 2, you know, but the other 3, they could be, I don't know. Osama bin Laden, I wouldn't even care. They're very tolerant people if you ask them. However, the result is a very highly segregated neighborhood. Now, one solution to that would be like people are lying to you. Obviously, they're lying. They want to say are tolerant there. Now, but that is a very persistent phenomenon. So Schelling sat down and said, well, how can we actually work it? So I show you a little computer simulation of how we can play with it. That's a segregation model here that I have. And we can set up our society. You can see it as 3,000, 2,300 people, and I set it up. Oh, I set it up, and here I threw my people on the floor of my neighborhood. I have the red and the blues, right? The Republicans and Democrats, black and white, whatever you want. And I say, let's say they want to have 50% similarity. So what these agents do now is I set it up, and if they are not happy, here's my happiness index. They keep on moving until they find a neighborhood where 50% of the neighbors are exactly like them. Right? Here we can see right now, okay, 50% of them is similar and 42.8% is unhappy. That means, okay, they're probably going to move around, right? They move around until they find a place where they are happy at the end, right? Okay, you ready? Let's see what happens. Go a little bit down, make it a little slower, set up. I set it up, I set it randomly up, and then let's go. What we can see here is basically the similarity level went up quite a bit, the happiness level went down. So they kept on moving around until they find a neighborhood where they're quite similar. Until you find here basically, well, the unhappiness goes down, 0.2, 0.1, and then you finally find 0 and you found equilibrium. Somebody's still moving around, somebody's not happy here, over there. Now we are happy. Right? Everybody's happy. However, you find 87% of the neighbors are similar now suddenly. We only wanted 50. We only wanted 50% of our neighbors to be happy, but actually the result is a very segregated neighborhood, as you can see here. We can run that again. Maybe that was just a mistake. Let's try that again. Try it again. The unhappiness level goes down. Many people are happy. They move around until they're happy. The similarity level goes up here, and you can find that, accelerate that a little bit, until you find equilibrium. Again, we are at 86%, correct? And you can run that many times. You can do that slower. These are these. I don't know if you remember SimCity, for example. That's what you do. Basically, you simulate, and you can do that all the time. Interestingly, you get always a little different result, but at the end, you get an invariant distribution. How do you call that? You get a kind of like in the same ballpark. And some of these things are path dependent. They depend on the initial conditions, which in this case are random. Okay, let's see how it works. We could go, for example, here now to 45%. Let's see what we get. Run it again, 45% set up. We went down a little bit, not really, now we're at 85. Try that again. 88, actually now it's higher. Maybe you have to go a little bit down. Let's go to 40%. The level is, well, 82. Now we went a little bit down, correct? So now you can play with this and see which kind of segregation you get at which kind of level. Let's put it here now at 26. That means I want 1 out of 4 neighbors to be like me. The other 3 could be completely different. I mean, that is really a tolerant society, right? Let's see what we get. Quite good. 65%. 65% similarity only. And you can still see it's a very, mixed society, you can see now. 65%, pretty stable, correct? Now let's go down to 25% similarity. What happens? I dropped a lot. So I only changed 1 point from 26% to 25% in my tolerance, but I dropped only almost 10% in my segregation of the outcome model. So at this point, here's a phase transition, right? That's one of these nonlinearities. That's something that traditional statistics could not show you because it would be linear. I suddenly have a drop, right? Water became vapor. So you find these kind of phase transitions when you play with these simulations. We can do that at the other side as well. I have here 75% of similarity. What I get is, whoa, now they're looking around. There's still many people unhappy. They want 3. Look, they want 3 of the neighbors to be like them. That is quite. And now we found equilibrium, 99.9%. 99.9% of them is similar, right? We can run that again, and you can probably see that 99.9%. So here that happiness goes down, the similarity goes up. They're still not happy, and here we found unhappiness. Let's put it to 76%. Let's see what happens. What happens? They don't find equilibrium. Because they're all so racist that nobody of them is really getting happy ever. So actually, but the result is a very homogeneous society, right? 50% of the neighbors are always similar. But they're all acting around so much.
Is it possible to instead start with the happiness, try to maximize happiness? Maybe there's a point where it keeps rising up to a certain point and then it falls?
You can check that out, and that depends a lot of how you define your model, of course. So this model is very simple. I just say the 4 neighbors around me. That's why I also have these 75%, 76% tipping points. You can make this model much more complicated. I could put networks in. I can say, well, on average in your neighborhood. I could say, actually, the network connection, it doesn't matter who is your neighbor, it matters how many people are in your hood, and so forth, and then really make this model much more complicated. But there is something very interesting that I wanted to show you here. It's something very surprising, right? A bunch of people who are not tolerant at all, suddenly through a tipping point, 1% difference, gives us a completely different outcome. And that's basically what shows you that people are so extreme that they don't find a tipping, that they don't find a consensus. And that leads you to these kind of like general models that you now come up with, that a bunch of tolerant people actually leads to a lot of separation and segregation. Now when people are separated and segregated, polarization sets in, they become even more extreme in their opinions. While they're more extreme in their opinions, they develop extremism. Now once they are as extreme as they are, they never find again an equilibrium, so they become more a mixed society, which again breeds tolerance, which then you can say societies work in these long cycles, right? Which right now many people say America becomes much more polarized and then maybe becomes more tolerant and so forth. So you can come up with these theories, if that's true or not, I don't know. But these are kind of things that I showed you. And the interesting thing is with these computer simulations, you come up with amazing results which are quite surprising that you usually couldn't see before. So what you can see here is, first of all, the total is different than the sum of the parts. Because you have these phase transitions, right? You have to look around corners. And there's a dependence on initial conditions. Yeah.
Since we know that Emergence is not a fixed feeling, someone can adapt easily to this neighborhood. What would be the margin of error when you use this kind of...
That's interesting. You can make your Asian-based models now as complex as you want, right? You can now say you introduce diversity. So not everyone has the same threshold. You can say some people have another threshold. Now the thresholds can also adapt over time, like it is in reality, right? I can say, well, if I'm there and there are two here, then my threshold changes over time, so you can program that as well. You can create diversity between the agents, and you will get very different outcomes. At the end, what they do nowadays, they really feed these agent-based models with big data. So that's the merger between the big data with real-time data and computer simulations. And if you talk with the guys who do these agent-based models, they have no doubt that in a couple of years, the entire White House will actually consist of big computer rooms, each one with a different database fed, where they in real time simulate society and find out what's going on. Right? So the Twitter data come in and then they simulate it, and then they have different probability distributions where they say, well, that's what we're going to do, Commander-in-Chief. You see that, press this button or not. So that's basically what they're working on. They simulated that a lot with the diffusion of diseases, for example, as well. In the SARS virus, they fed the agent-based models with real data, and they could make very well predictions of where the virus will spread and where not, and which airports they had to watch and which not.
This residential mapping, in a sense, doesn't take into consideration real-world concerns like location of schools or people not being able to afford the house they want in the neighbourhood they want. So it's not. Isn't there a danger of like that becoming a reality when actually the reality is a lot more complicated?
That's always with models, right? So models are always an abstraction from reality. So the only working model of the universe is the universe, full stop. Everything else is an abstraction. Now, if you really want to predict the future, you would have to rebuild the universe with every atom, every molecule, every butterfly effect in it, and then you could make predictions which are accurate. Now, it's highly inconvenient to carry a universe with you, so we have to abstract, right? Now, this is very simplistic abstract. Now, however, this was tested to be very, very correct in many, many cities, as simple as it is. And he got the Nobel Prize for it. So it's very, very correct. However, you can make it more sophisticated by programming your landscape. You put a real city in here. LA. I think in LA it was actually modeled. And then you put real diversity. You program the agent according to your census data, right? And then you see what will happen. You get closer and closer. But you can never completely, no model is 100% correct, yes. So one of the most fascinating things out here, they said for Los Angeles, Milwaukee, Cincinnati, Omaha, and Kansas City, they showed that it works perfectly. So here he is showing one of the most fascinating things with these agent-based models for me is that they help me a lot as well if I want to explain these things to policymakers. That's what I find right now in the US. So when Schelling actually did this thing in the 70s and in the 60s, what this old guy did, he sat on a table on a chessboard with pennies. And he played around with the pennies and he saw these patterns emerge and he didn't have a computer. And in his book he writes, I cannot too strongly urge you to get the dimes and the pennies and do it yourself. There's nothing like tracing it through yourself and seeing how the things work itself out. In an hour or so you can do it several times and experiment with different rules of behavior, sizes, shapes, and forms, and so forth. And then he drew out with a lot of pain this kind of graph. It's an equilibrium graph. And he said, well, this goes here, this goes here. So if you're on this side, you find this equilibrium. If you're on this side, you find this equilibrium. Now, if I go to a mayor or to a president or to a policymaker and say, Mr. Policymaker, let's sit down for a couple of hours with some pennies and work it out ourselves. You see how they emerge, you know. Or if I say, Mr. President, look at this graph, that's the equilibrium. I need a couple of $1 million because that's the equilibrium. You see that, right? And that's why we need a couple of $1 million project. I don't know if we're going to win any support. So what's the other solution is what economists do is game theory, you know, differential equations. That's the same thing, that's the same equation from a microeconomist. And he says the equation might be read as follows. The expected fraction green next period is the fraction of green this period, minus any greens who change place with the blue. The second term on the right hand side clouds, any blues who change the place with the greens. So, Mr. President, as you can see this differential equation, what I do, I just solve it. I take the derivative, I put it equal to 0, I get to the maximum, a couple of $1 million now in order to do this, because here I find the optimum. Maybe the intern can follow me then, right? With a lot of luck. But anybody who has something to say will most likely not follow me. So the cool thing now is with these computer simulations, they don't only help me to make sense of things, but they really also help me to show how these things work. And they're pretty intuitive once you play with them. Right? So from a policy side, it makes a lot of sense to play with these kind of things. Let me show you another one, and then maybe you're interested in that. That's called Rebellion. By the way, this software you can download it and play with it yourself. It's called NetLogo. And you can play with these different models. They're all here described. You just go into info, you describe this different model. So this model is a model of rebellion. You have people here who are quiet, jailed, or active. People wander around. Actually, let me read it to you. The population wanders around randomly. If the levels of grievance against the central authority is high enough and their perception of risk involved is low enough, they openly rebel. Separate population of police officers acting on behalf of the central authority seeks to suppress the rebellion. So let's play with this around a little bit. I have a cop density, I have an agent density, I have here my model, and I see here that some people are active rebellion, then they go into jail. Now if they're jailed, when they come out of jail, the rebellion picks up, right? The red goes up, and there's a quiet population that basically fluctuates with that as well. So you can basically track how many people get jailed. You can now put your cops, how many cops you would need to suppress the entire thing, or you can ask the question, what do I need to begin a revolution? So let's check that out. We have here government legitimacy, let's say, of 90%, so many people love the government, right? And we set it to run. Let's put on the speed a little bit, set up, and we run. And we can see, well, many people are quiet and active, there's actually nobody here. The government legitimacy is very high. What happens if I bring the government legitimacy down a little bit, right? I go slowly down. And they got, oh, now a little riot broke out. Some people went. But then they got jailed. You can see they got jailed. The black one went out. Oh, there are some people, but now they got jailed again. Well, I have them all under control, right? The black is above. There are more people jailed and they're rioting. The government legitimacy goes down. And here, well, I have them still way in check. Here you can see, well, if every time it breaks out, many people then go to jail. So the red one as well are the ones that are active rioting, and the black ones are the ones that are jailed. Now, I can see actually, well, the majority of the people are still quiet. And I let my government legitimacy then go down. Maybe you can accelerate that a little bit. Yeah, some riots, but now, well, it's quite many people are jailed, right? Much more than they're quiet. But the government legitimacy is below 50% already. 38, 37%. Actually, well, most of the people are jailed. But actually, no riot breaks. I like the rioters cannot overthrow the government, right? Because they are still more quiet, and the active ones are actually lower than the jailed ones. So now here I have a government legitimacy of actually, wait, 0. Actually, it's 1% government legitimacy. Most people are in jail. It looks a lot like maybe Syria or something. And here we have active rioters, we have very little, and most of the society is still quiet, right? So that what happened when the government legitimacy went down very slowly. Now let's try the same thing again. Let's have the government legitimacy here at 90%, that's how we started. And we have the setup, and we go, and we run, everything is very quiet. And now suddenly, let's move us down to whoa, whoa, whoa. So what happened here? the entire country was suddenly on fire. And we went down to 65% only. So the government legitimacy is still at 65%, but here the government was clearly overthrown. There were many more rioters than there were quiet people, and the people were not in jail yet. So if you have a friend who wants to overthrow a government, tell him it serves him much more to have government legitimacy reduced a little bit, but very quickly. If you do it slowly over time, it's kind of like you put the frog into the boiling pot, right? You won't even notice, and even so at the end there's a government in charge who nobody really wants, it's still in power. So these are the kind of things you can really play with, and you can look for the tipping points, and you can look how that actually evolves and what happens, how many police people, I could now, we run out of time, play with the police and so forth. And actually what you can do then, you can grow very sophisticated society. So this is a society here, an economy, for example, for the people who are interested in economics. You can really have a society with different season, migrational patterns, inheritance. You can test for tax incentives or trade patterns. You can see lending and interest rates, how that affects the economy. Pollution. For example, you have pollution patterns and see, well, this results pollution and this not. And so what is if I tax the pollution, what will happen? And basically what we do nowadays, we play computer games all day long. And with that, we hope to find out interesting things of society. All right, 5 minutes, please.
Do you have a model of electoral systems and the amount of people who vote? The relationship between the voting numbers?
Yeah, I saw once one. I don't have it here now. But they're also, like for example, in this net logo, that's kind of like the SPSS of agent-based modeling. It's very easy to use. You saw that now. There are hundreds and hundreds of models. So actually also what we do is not like I sit down and program it from scratch. I look out if there is a model and then I start to modify it a little bit and then I play with it. And it's a very intuitive programming language. It's really like you have these agents and then you put in cars and the cars will appear. So it's as intuitive as a programming language. And then you change these. And many of these models are very similar. So diffusion models, diffusion of innovation, diffusion of disease, diffusion of rumor, diffusion of opinions, political opinions. You use kind of like a similar model, right?
I mean, well, this is fun and fascinating. Isn't it also a bit dangerous if you add too much significance to it, because there's so many variables, like we've already mentioned, that are not taken into account. People are not the same. Some are very charismatic and could be community leaders, start social movements, and actually, as long as they're not jailed, they could actually make a significant difference there. That's not part of the model. There's just one example, but there's so many.
And absolutely, that goes back to the same thing.
Interdependencies between some of these.
Yes, and that is always the danger in all science. So in all science, you can have two things. Just let's say we try to do science. So what we did in the past, as I said, remember Weaver, he said in the past it was we modeled it like with 2 or 3 variables, and we just said there are 2 or 3 variables: voter opinions and government legitimacy. And then we wrote a differential equation because that's a differential equation we were able to solve. If you put in a 3rd variable, you could never solve that thing. Or the other thing is we just make assumption statistics, we describe it, and say in the past that happened, so that must happen in the future. Which we also know doesn't really work, right? Or you make a case study and say, oh, that happened in this country, so it must happen. Yeah, so that's always a danger. Now with this, actually that's the most flexible scientific playground you have, because you can do everything. Still, there are still equation and rules, and the equation and rules are basically here. So see how many. If I would publish a paper with all these equations and all these assumptions, all these things, so that's my code. That's the code with which it is programmed. And I can change it. I can put more diversity and less diversity. It's still science. It's just that the equation, the model is much more complex, and actually that's the most complex model I can build. With my differential equations I couldn't do it, with my descriptive statistics I couldn't do it, and with just thinking about it, it won't work, because if I just think about it, I could never think around these corners. The nonlinearities, they will fool me. Right? So I actually have to play with it, and these surprising things come up that you would never find. Now, is it 100% certain? No, because as I said, the only working model of the universe would be the universe. And that's not it. However, if you do these things, what you come out with, I run these things, of course, 10,000 times. And at the end, every time it's a little bit different, and I get a probability distribution. And what happens at the end, you go and say, Mr. President, if you do this and this and this, with 60% probability, that will happen. With 39% that, and with 1% that will happen. It's very unlikely, but it could still happen. And when it happens, I still told you so, but it was just very unlikely. Now, well, that's only humble and fair, because that's how these probabilities comes in, because I do not consider everything in my model, and I cannot. Right? I just have to choose.
This kind of modeling is how they're doing a lot of war games analysis.
Mm-hmm.
For instance, on the Korea dispute, there are different escalation scenarios that have been worked up about what kind of actions prompt what kind of responses, and how you keep most of the deaths that occur on the north side versus the south side. And what the US learns is a preemptive escalation model is the only way that most deaths occur in the north. So it's like a real working interaction of all these presumed scenarios.
Right.
I'm fascinated by this scenario, especially this tool that enabled you to plan them out. And I wish I was smart enough to use them in capturing my ideas and my situation in real life. I will definitely take a look at it and don't go and start playing around the scenarios. But the larger framing of my question is that everything you told us seemed, in my mind, seemed to be counterintuitive to what you think it would be on a much more, should I say, linear pattern as opposed to a lateral view of the world. And I like the quote about the only way you can, the one about the universe. The only working model of the universe is the universe. So are there still bits and pieces of that model that we don't understand, that in another 100 years, perhaps from now, this will just be like it was two-dimension 50 years ago? The other part of it that I was also find fascinating is, something like Darwin's stuff I really don't understand, like chaos theory, for instance, and you're reading that, and you read about entropy, you read about all this various interesting stuff. And I'm looking at my city, Lagos, which is, 17 million people, but somehow it functions. So my own imposition of some order was, I described it as structured chaos. Each time I talk about structured chaos, it seems like a contradiction in terms, because you can't have chaos and it can be structured. But I now know that it is. The other thing that also fascinates me is the issue of fractal geometry. And how does that, how does that fit into this, working model of the universe? Do the parts actually reflect and organize the whole? And what is the relationship between the parts as both of them evolve? Are we really little bits and pieces of us the same everywhere else?
Might be. Now, the fractal geometry and also what basically called power laws are very frequent in complex systems. So just because they emerge because of the interaction. So actually, complex systems are often distributed according to a normal curve, but often to a power law. And these power laws are very fascinating on one side because they have this structure, other as well because they are a nightmare for an analyst because they don't have an average. They don't even have a standard deviation. They are scale free. So you cannot have to say on average, So, and they come out of this. Now, but not every complex system is distributed according to a power law. They're very fascinating. And many of the power laws that complexity scientists said they're power laws now turn out not to be power laws. They are log normal or whatever. That's why the joke is nowadays like log. What's there is a power law because the power law goes to log. But it's not a power law most often, maybe log. So we test for that. And so there was a lot of course, this fractal geometry gives you the pretty pictures and it's fascinating and the fascinating properties, but many of them don't turn out to be. So for example, now in my lecture as well, I have the power law as the last lecture and it's like advanced topics, but they created much more confusion because they are so cool to what they really help us. But yes, it is a very important distribution. As normal, the normal distribution is very important, Poisson distribution is very important, and power laws as well. But it's not like, it doesn't have to be a fact. Of course, fractals are very cool tricks. You just do the same thing on different scales, and you get a scale-free dynamic, and that's often how it works, but not always, yes. Yeah.
Other questions?
You work for EPLAC?
Yeah.
And do you use any of this in your work?
I hope I will. As you guys know, the UN and other structures, it's not like they've been waiting for me to tell them all of that. But they started to listen, and I'm trying to convince them. I think I will start with collecting network data. This is the first part of it, because that seems a little bit to them like, it's a little magic, but so I push them to collect network data, do some studies there, and then hopefully further.
I have another question. I suppose you're following this post-2015 development agenda debate. Is there any of this that could be applied creatively to shed light on the interdependencies between making progress on one goal versus the other, because that's one criticism of the Millennium Development Goals, that they were so silo oriented that we didn't really account for how progress in one area could have great synergies for another area.
You notice the weave, Luis is also with the UN.
Yeah, yeah, it would be interesting. I mean, you would just start to grow these artificial societies. Also, when you want to read about, there's these two books I would recommend. One is called Growing Artificial Societies, and the other one is the one from Schelling, Micromotives and Macro Behaviors. And yes, so what you could do is just do this. You know, you would certainly start very simple. I mean, we cannot simulate the world, but you can say, well, if there are trade-offs, I try to program them and see, okay, so education and income or this and that, then you try to put them together, you have to put the relations, and again, at the end it's in the modeler's mind, it's in the scientist and the analyst's mind, what you put in and what not, and then you can start to model. And then you go back, you see how it works in reality, but you could. Actually, yeah, it would be very fascinating.
I think one of the areas that's very much debated right now is the inequality goal, whether to have an inequality goal or not. And one argument is that, according to research, if you work on inequality and distribute wealth within a society, you will be much more successful in cutting down on maternal mortality and hunger and all kinds of much faster than in societies that stay very unequal.
Right.
So it's a very powerful research and powerful knowledge that it remains to be seen whether it's going to be taken seriously or not.
And that's what you do. So in this book, they work with this sugar scale economy, basically. You can see that. So you have all these interdependencies here, right? So you have lending and interest rates, then you have the pollution, and then you have how disease diffuses. So if you would like to do that in one paper, you know, in a journal article, to have this model, it would be like, oh, you have either a model on disease diffusion, or on taxes, or on lending, or on interest rates. But bringing all of that together on pen and paper would be too complex. Now you do that here, and you just see what happens. And sometimes things happen that you have no idea where they suddenly come from. So you play with them for days, and then you start to get a feeling for, oh, that's how it works. And at the end, it makes also sense, right? Now, you grew it. You grew that artificial society. So then you also have to understand where it comes from. You don't always. Sometimes you grow stuff, you still have any idea where it comes from, but then you can do science with it. I just knocked one out. I said, let's take out the interest rate. Does that change anything? No, the interest rate has nothing to do with it. So I knock out it, and you know, you can do experiments. I cannot put society into my lab and play with it. So what I do is I simulate it. And then I can do science on it. I knock it out, I put some in, and so forth.
You said you can do simulations of various types, like building on the question that Louis just asked about inequality. The other variable that is being considered for the post-2015 goals and targets for the social indicators is governance. And there is a discussion about whether governance should be an independent target in itself, or whether it should be a cross-cutting issue which affects everything else, like it affects the health and the education outcomes and so on. So can your model tackle that kind of two alternative scenarios to simulate?
Sure. So governance, it depends on how you define governance, right? Here I have, for example, institutions, or let's say interest rate or lending practice and so forth. This is also governance, inheritance laws, right? So the inheritance laws or not, and you can see that the income distribution will change if you have inheritance or not. What do you do with this model? So what I did with my students the other day, we played a lot with, oh, you put inheritance of money, and then you put also you inherit your debt from your parents. Oh, that changes things a lot, right? And then you put an inheritance tax on it, and that changes. And then you can shape income distribution. It's not like the Pareto law is God-given. You create that. So you can also, if you want, bring it out. And you have many different tools now you can bring it out. And that here then, this here measures the income distribution. You can see whatever income distribution you want at the end, right? You can play with this. And so also governance structure, as you saw in the other one, how many police force I have. And how many police force I need, and how many this is here, and you know, and you can play with it and then set up what is the governance, what is the institutions you need.
This tool, apart from the logo, I mean, the whole body of knowledge, where can we find it? On your site, or on UN site?
No, actually on my site, no. I went around for 5 years and collected bits and pieces. I studied a lot with the engineers, a lot of engineers do these things. So actually, I think if you're interested at the Santa Fe Institute site, there are some cool videos on there. So the Santa Fe Institute does a lot. If you want to read about, especially this agent-based modeling, these two books, the Epstein and Axel, Growing Artificial Society, and this book here, Micromotives and Macro Behaviors, is are two very good books. And yeah, I think if you go on the Santa Fe Institute site, you find a lot of videos with these things that go around there.
All right. This is absolutely fascinating. Thank you so much. Okay, we will reconvene in the other room for Nick in 5 minutes.